Hello students, welcome back. In this part, we are going to discuss about some famous reactions shown by aryl halides. Those are known as ring substitution reactions. So let's see what are those. So in the previous part, we discussed about some chemical reactions shown by aryl halides. Now I will discuss the important chemical reactions shown by the aryl halides, that is the ring substitution reactions, which are important for JEE purpose as well as for the competitive exams. So yeah, I am showing some ring substitution reactions which are important: halogenation, nitration, sulfonation, Friedel-Crafts alkylation and Friedel-Crafts acylation. So these are 5 ring substitution reactions. So let's study these reactions in detail with the mechanisms. The first one is the halogenation. So what is halogenation and how it takes place? So halogenation is nothing but halogen is added to the benzene nucleus. So we are simply halogenating benzene, halogenating an aromatic compound. So halogenation takes place in the presence of iron or FeBr3 or anhydrous aluminum chloride as a catalyst. So here it is important to use a catalyst, and we'll see the functioning of catalyst, why it is necessary to take catalyst for the reaction to take place. So here benzene we are taking, and we are taking bromine, we are seeing bromination particularly. So I am taking FeBr3 as my catalyst. Here the bromine Br2, this is a non-polar bond, right? So it doesn't break easily, it's not polar. So there should be something that should make this bond to break, right? So who is this guy that helps in breaking this bond? That is nothing but this FeBr3. Let's see how it happens. So yes, if you see, FeBr3 is actually Lewis acid, right? And if you take FeBr3, AlCl3, these are all Lewis acids. So they need electrons, they are electron deficient. So we are making this bromine electron deficient by giving its electrons to FeBr3. So it is having 3 lone pairs. So one lone pair it will donate, one lone pair it will give to this FeBr3. So it is Lewis acid base reaction like this. So by donating its lone pair to this one, so here bromine will get a positive charge, right? So halogen does not bear positive charge, it always bears negative charge. It doesn't bear positive charge due to its high electronegativity. So this positive charge present on this bromine atom makes it unstable. So what it will do is it will quickly take this bond pair of electrons and it releases Br plus. It releases Br plus. So it go away as FeBr4 minus and it releases Br plus. So this is actually an electrophile where the benzene is a nucleophile which attacks this one which is electron deficient. So this bond forms and this bond is going to be broken. So as a result, what happens is we will get this one. We will get this one. So here the benzene has lost its aromaticity, right? So it should, here it has 4n plus 2 pi electrons or 2n plus 1 pi bonds. So which makes it aromatic. So aromatic compounds are stable. So here benzene has lost its aromaticity. So it wants to gain back its aromaticity, which it will do in this step. So they actually Br minus. So this Br minus will take away this proton and this bond comes in. So it gains its aromaticity back. So it is stable again. So here we simply halogenated the benzene and we have taken bromine as well as the Lewis acid as a catalyst. So here it is acting as catalyst and we have seen the functioning of that FeBr3 here. Okay. So this is the halogenation, especially the bromination of benzene we have seen, right? So other reactions are also more or less the same thing. So what will vary is the Lewis acid will take different or the species will take different. Here this is halogenation, so we are taking bromine. So if it is nitration, we will take some other, right? So but the mechanism is more or less it's not going to vary much. Only the members will vary. So next is a nitration, which is also a ring substitution reaction. Here we'll take a mixture of nitric acid and sulfuric acid. Here we don't take any catalyst like AlCl3 we have taken in the previous case, but we'll take HNO3 and H2SO4. So the first step is a generation of electrophile. So first step is generation of electrophile. Second step is the attack of benzene ring on the electrophile. The two steps. So if you say this is HNO3 nitric acid and this is sulfuric acid. So this donates its lone pair to, it will abstract the proton. So as a result it will get this one. So this is OH2 plus. So it goes away by taking this bond pair of electrons and will get this one, which is nitronium ion NO2 plus. Will get this nitronium ion. Okay. So this is the generation of nitronium electrophile, and the second step is the attack of this nucleophile on this electrophile. So it attacks this electron deficient center and we get this one, so which is not aromatic. So it gets its aromaticity back by losing this hydrogen. Okay, so by losing this hydrogen, this bond comes in and it will get the aromaticity back. So here we nitrated it. So we simply added NO2 to the benzene ring. Okay, so it is actually, this is not substituted one, right? So if any substituent is there and that substituent is going to direct the nitro group to only one specific position, right? Here it doesn't matter, like it may come here or it may come here, it may come here. Okay, so but if at all any substituent is there, like if I take this methyl, so here the NO2, it preferably goes to one particular position, because this CH3, it directs the NO2, directs the electrophile to go to one specific position. So we get that specific position as a major product and the other position will get as minor products. So this is the more about the ring substitution reactions when there is the presence of activating groups or deactivating groups are there. Okay, so if it is an activating group, electron releasing group, then it will be ortho para director. If it is a electron withdrawing group, then we will get majorly meta product as the dominating product. So this is the nitration, and the third one is the sulfonation. So sulfonation, here we will take H2SO4 only. So H2SO4, so first step is a generation of electrophile, that is this OH, this donates its lone pair to this one, it abstracts the proton and we get this one. So this bond breaks and there is a formation of bond over here. So we will get this one, which is SO3H. SO3H plus is the electrophile here, right? HSO3. So this electrophile, the benzene will attack this electrophile and you will get this benzene sulfonic acid as the substituted product. So in sulfonation we add HSO3 to the benzene ring. That's what you need to remember, and you need to remember what are the reagents that we are taking. We are only taking sulfuric acid, right? In nitration we have taken nitric acid along with sulfuric acid, but here we are only taking sulfuric acid as the reagent. And the fourth one is the Friedel-Crafts alkylation reaction. So it's a very, very important reaction which is mostly asked in the exams. So let's see what it is. So here it is alkylation. That means an alkyl group is added to the benzene nucleus, right? So for that we'll take an alkyl halide along with the Lewis acid, the catalyst, that is aluminum chloride will take preferably. So that is anhydrous AlCl3 will take. So the reaction, the first step is the generation of electrophile. So this chlorine, in order to break this bond, so this AlCl3 is used to generate the electrophile easily. So this bond breaks, you can see here this bond breaks and you will get this carbocation as the intermediate and this carbocation as the electrophilic intermediate. So the benzene, which is a nucleophile, attacks this electrophile and this group is simply added here. You can see this group is simply added here. So if I take methyl chloride, so I'll get toluene, that is methyl benzene. If I take ethyl chloride, I'll get ethyl benzene, right? So like that. So this is a Friedel-Crafts alkylation reaction, and then the last one is the Friedel-Crafts acylation. So which is also more similar to the alkylation, but the only thing is here we are taking acylation. We are taking an acyl group, right? So that is, instead of taking an alkyl halide, we'll take an acyl halide. So RC double bond OX, which is an acid chloride, acid halide or acyl halide. So this will take, right? So that you can see here, RC double bond OCl we have taken, and this is the electrophile that is generated here. So this bond breaks, this lone pair comes in, and you will get, here you are getting CH3CO plus. This is the electrophilic intermediate, and which is attacked by benzene, and as a result we will get this one. Okay. So if you take, so simply this is going to be added to the benzene, that's all, right? So this R may be any alkyl group, so simply you need to add this thing to the benzene ring, so which is known as Friedel-Crafts acylation reactions. So this is all about the important ring substitution reactions, starting from halogenation, nitration, sulfonation, Friedel-Crafts alkylation as well as acylation. So this is about the chemical reaction shown by aryl halides. So next part we'll discuss some brainstorming IIT JEE, previous IIT JEE questions. So students, in this part we discussed about some ring substitution reactions of aryl halides, which are namely sulfonation, nitration, halogenation, and Friedel-Crafts alkylation and acylations. So in our next part, we'll solve some previous IIT JEE questions.